So there's a light flashing here. Does it mean the battery needs changing? Can you just check?
Okay, the battery is...
Thank you. Okay, so my task is, first of all, to walk you through the various input changes that you need to be aware of when you try to run a CDCC calculation. So just to remind you, Antonio talked about cluster models and how do we include excitation of the projectile first to the bound states and then to the continuum. And what you're going to do this afternoon in the homework is divided in two sections. One section where you do single particle excitation to a bound state, and then the second part where you actually include the full continuum and do a full breakup calculation. So in order to do the second part, this is going to be what I'm going to first talk about. That is, how do you actually, what is the input that you need to be aware and put in so that Fresco understands what you want to do. And then in the second part of what I have today for you is just walk you through an example of a CDCC calculation, looking at the various details that you should be aware of. Okay? So just to make sure that we're all on the same page, Antonio went through this, so probably after the break you still have it in your mind. What we do is we start out with a three-body model. So it's a three-body Hamiltonian for projectile and target. The projectile is split into two clusters, and so what we try to account for in CDCC is the solution for this three-body problem. So the Hamiltonian is a three-body Hamiltonian. Then we get a three-body scattering wave function that is expanded in the projectile states. So there's an internal Hamiltonian for the projectile, and we expand in those states. And so the three-body wave function, in principle, if those states are complete, should be exact. Then the projectile, of course, in this formalism so far, we've assumed that there's a very simple formulation for this clustered projectile in terms of single particle states. So we're not including all the many-body complexity of this projectile. And then there are optical potentials between the constituents that is usually taken from elastic scattering, which is the sort of thing that you did last week. Okay? So now, what does an input from Fresco look like? Well, I will show you the full input in a while, but let's start by discussing, and I have the feeling that the contrast here is particularly bad. The lights, anybody knows how to work with the lights here? Jeff, you seemed like you knew what you were doing.
The front lights?
The front lights, get rid of them.
Yeah.
Because I think, because I'm going to be talking about details of the input, I'm not sure that this is as legible as you'd wish. At least from the back I was having trouble. Oh, thank you. That's better, right? Okay. So this input is not an input to the Fresco directly. In fact, there's a version that you can use it as an input to Fresco directly. But the way we're going to do it is run it through a preprocessor to generate the standard Fresco input. Okay? So this, what it does, what this little code does, it's a nice little script that just it basically generates the bins for you. And so you don't have to do it by hand yourself. However, you still want to have control on what you're doing, and that's why I want you to generate an input that's the standard input, so then you can look at it and see what you've done and make sure that what is there is what you want to be there. So what we'll do is go through this input in some detail so that you will be able to prepare your own for this afternoon. So let's start with the first section. It's a name list called CDCC. And so that's sort of a method name list. It has all the details of the method. And if you think of the standard Fresco input, there's a name list called Fresco that is the name list that usually contains the sort of information. So if you remember, HCM was a step size for the radial integration. R match was the maximum radius, the radius at which you stopped your integration and did your matching. Now here there's a new thing called the RSM. So this is the first difference that I have to point out. When you do a breakup calculation, you deal with bins, scattering bins that Antonio just showed this morning and you saw earlier last week. The bins wave function, even though they're square integrable, they're still relatively long range. You get the oscillations damped, but you still have them extend large distance. In addition, when you solve these coupled channel equations, where you put in these couplings between these long-range bins and the interactions, you end up with long-range couplings. So you really do need to include those couplings to very large distances. Now, you don't want to integrate your equation all the way to 1,000 Fermis or anything like that, right? The number here is 1,000 Fermis, RSM. RSM stands for R asymptotic, and that's the place where you think, I can safely ignore my couplings and match to my known standard H minus minus SH plus, you know, the standard asymptotics that we discussed. There's this region where it's Coulomb long-range couplings that are coupled. So there's various channels now, and you get coupled Coulomb functions. This region is a region where Fresco knows the form for these, and so there's a separate routine that handles this part. So it's important for accuracy when you do breakup calculations or any other calculations you can think of where long range is important. This is a way of handling that without being punished in terms of the time of your calculation. So you're not actually integrating out to 1,000 Fermis, you're integrating to 60, and then you're using the smart coupled Coulomb functions constructed in a given way. I don't want to go into the details, although I'm very happy to discuss it with someone if you're curious about it. And then it's sort of propagated out to 1,000, where the matching is done in the usual sense, in the way that we discussed. So you will have to put R match negative so that it knows, it's like a switch, it knows that now it switches onto coupled Coulomb functions and it carries it out to RSM. Is this point understood? So this is one detail that is added on to what you had before. I think the rest of the stuff is similar. The laboratory energy is given, and you see it's relatively high. In this case, it's an example for boronate breakup on lead-208. Boronate is very loosely bound, and so it breaks up very easily, and that's the example that I picked here. Jmax. So if you look at this, this is a smart way of not having to calculate all your partial waves. It's a high energy calculation. As a high energy calculation, you need to include many partial waves. Hopefully you've figured out that higher energy will immediately translate to a higher Jmax in your sum. And so here it's 9,000 that is needed. That's quite a large number. So if you have to calculate all 9,000 partial waves, it's going to take a while. So there's ways of interpolating between these. And what this J-Borden jump does is it has a way to jump over certain L's and interpolate between them. So from 0 to 200 partial waves, it doesn't jump, it calculates them all. From 200 to 300, it does it in steps of 10. From 300 to 1,000, it does it in steps of 50. And from 1,000 to 9,000, it does it in steps of 200. So that's what it does. I mean, you can decide to do your calculation fully with all partial waves, but then you might be waiting for a while, and so this is a way. Of course, it has to be controlled, and you want it to do it in a converged way. So you can't necessarily jump at your leisure. You have to jump in ways that still gives the same answer. Okay? So do it controlled. This line here gives you the grid of angle, the angular grid for calculating your cross sections. So the reaction we're talking about here is a relatively high energy reaction. It's forward angled. So most of the cross section comes at the forward angles. You don't really need to calculate all the way to 180 because everything outside 20 degrees is actually not contributing to the cross section. So in this case, the cross section is calculated only up to 20 degrees. This needs to be adapted for per case, right? So there will be, we're now in the realm where the calculations can get pretty large, and so you need to start thinking efficiently. You can't just brainlessly put all the parameters, do everything, and then you might be waiting for hours instead of actually getting on with the homework. So 20 degrees is what is done here with a very small step size because all the information is at the very forward angles. So in this particular case, we wanted to know what's going on at those small angles. There's an additional feature here that I think hasn't been introduced yet, and that is when you have high energy calculations, you've got these large partial waves. If you think of a centrifugal barrier coming from L equals 9,000, it is going to be a pretty large centrifugal barrier, and that means if you start your integration at the usual point, you're going to be integrating zeros, right? Basically, your wave function is zero there because you've got such a large centrifugal, such a large repulsion. So that introduces difficulties in the numerical integration methods. And so a way to avoid it is to just shift that place where you start your integration. And so what cut R does, it just cuts, shifts the place where you start integrating, and it avoids these small r's and the strong repulsive potentials. So in particular, minus 20, what it means is it puts the starting integration 20 Fermis inside the Coulomb turning point. And so there's a way to do it. Now, if you want to use different features, you have to go to the manual to see what options are there. But this is the problem it addresses, this variable. There's an additional line, and that additional line is the one that's really critical for the type of calculation you want to do, and so I give it a whole slide. So this line has a sort of physics of what's included in this calculation. NCool is a switch that allows you to either include both Coulomb and nuclear, or just Coulomb or just nuclear, depending on its value. REOR are different choices of the couplings. So you've got coupled channel equations that, if I don't have them here, but I can put them here so that we always remember what our equations look like. Let's say V00 minus E chi equals sum V alpha alpha prime chi alpha prime. Right, so you've got coupled channel equations that hopefully look, sorry, this should be the diagonal of whatever. I've pulled out the diagonal. Different from alpha. Okay. So if that should be what you have. And now you've got coupling potentials. Those V alpha alpha prime, V, depending on 1T plus V2T. I can't remember what notation Antonio used. So you've got two clusters, and it's the interaction between the clusters and the target averaged over your bin wave functions between cluster 1 and 2. And so these couplings have alpha equals to alpha prime. And so that's sort of reorientation in the sense that you ending up in the same state, you just changed perhaps the direction. Those choices, there's several choices on what you include there, whether you include them, whether you don't include them, whether you only include them if they're the ground state, whether you include them when it's to the continuum, whether you just don't include them when they're in the continuum. I mean, there's several choices, and so you'd have to go to the manual to see what you want to do about your problem, right? But that's what it means. Reor has to do with the choices of how you include the V alpha alpha, when the diagonal part of this interaction, of these couplings. Now, Jeff, if you tell me the button, I won't ask you every time.
Loom
It's Loom 1?
near you, the button your side, loom 1. See? Yeah.
Great.
So next one.
Thank you. Finally, multiples. Q has to do with the order of the multiplarity. Remember, we always expand our interactions in multiples, and so there's a truncation at some point. And in this particular case, it's everything up to 2. And you can test, of course, this is another convergence check. In your reaction, you may need to include more. It depends on the reaction. You may guess which is going to be the dominant one just from the spin and parity of the ground state. And so you may guess, it's likely the lowest orders are going to be more important, and then depending on the symmetry, you're going to have some things that are going to be more important than others. But you should always check that if you want a converged result, then that you've got enough Q's in your expansions. Okay, next, name list. So I discussed the CDCC name list, which has to do with the numerical method and what is being included in the equations, let's say. Then you've got this name list called nucleus, which basically contains information that relates to, in the standard input of Fresco, relates to partition, overlap, and states. Antonio this morning talked about this new name list called overlap that contains information about the bound state of the cluster that you're considering, or the continuum states as well. We had already from the first day talked about partition that had the information about charges, masses, things like that, and states that had the information of the spin and parity and energy of the various states that you wanted to include. So nucleus is a sum up of all of this in a very summarized way. It does not allow you the same flexibility. It is done specifically for one bound state and lots of continuum. Okay, so it's written in a way that's prone for the sort of CDCC calculations that we have in mind. And so you shouldn't really use it generally because there will be more control with a standard Fresco input. Okay, so what's defined here? It's a projectile. It's pretty obvious what I'm defining, but I'll go through it. So it's, I named it a boron 8. It's got charge 5, mass 8. It's got a spin 1.5. Now, anybody actually know the actual spin of boron 8? Anyone worked with boron 8 before? No? Anyone can think what should be the spin of boron 8, just given the number of nucleons? And should it be 3 halves? Do you expect it to be half integer? No, Jose? No? Right, it's odd, so total number of nucleons even, so you don't expect this to be the spin, and it isn't. This is a model that is taken here, and it's a model that comes from the consequence that we want to make beryllium 7 spinless. So beryllium 7 has a spin, it's 3 halves, and the boron 8 consequently has a spin that's not 0, it is actually 2 plus. And so you're going to end up with a description here that is an approximate description, right? So this boronate is not the real thing. It's in a given model where we neglect spin of this beryllium-7, and we're just considering the momentum, the angular momentum and spin of this additional particle, the proton. Okay. So we've defined a spin of 1.5 and a parity of -1. Binding energy corresponds to the separation energy between the proton and the beryllium-7. So the binding energy here is not the full binding energy of boron-8, it's the cluster binding energy, the relative motion between these two. So it's 0.137 MeVs. And then here are the quantum numbers that define the ground state of this nucleus as a cluster of a proton plus beryllium-7. So the ground state looks pretty much like a P3/2, and so that's what's introduced there. The core, the spin is not explicitly defined, but it is 0 because I haven't defined it by default as 0. The valence proton has spin 1/2, as I pointed out, this is included. And then there's a target, and the target spin 0. Okay, so any questions about the partition nucleus? The nameless nucleus? We'll go to the bin name list next. Is it sort of clear? So in the bin name list, what you have to do in addition, you already know how the cluster looks like in terms of masses and charges. What you need to do is now define how you're going to break up the continuum to include it in this couple channel formalism. So you need to define these energy bins or momentum bins, and the choice of either energy bin or momentum bin is done by this variable energy. That's either true or false. If it's true, it means it's energy, you break in even bits of energy. If you do false, then it takes the momentum. So it actually breaks it up in even bits of momentum, which turns out to be a different scaling, of course, with energy because of the square relationship. Then you define a start, step, and end for the grid. And this, of course, needs to be checked for convergence. So whether your step is very large, whether you include all states up to 4 MeV or 10 MeV will depend on the calculation you're interested in. Whether you break it up in 1 MeVs or whether you break it up in 0.1 MeVs will depend on the details of your continuum. And then you also have to introduce the spin and parity of the state, and the spin and parity of that state will connect to the ground state in some multipolarity. So it will depend on the dynamics you want to include in the calculation. Any questions about this name list? Okay, well, no questions is good. You'll have access to this afterwards in case you sort of lost, and we'll be around, of course, so you'll be able to ask us directly. Okay, so now the potentials. Now we've already defined the pot name lists in the standard Fresco input before, and here they're called potential, the name lists, but essentially they'll have this information. They'll have the information of the interaction between the various constituents of the problem. And if you think about it, you should really have an interaction, you should have 3 pairwise interactions clearly defined. But for the sake of Fresco, you also need something that's, as Antonio pointed out, you need something that's like an effective projectile-target interaction, because that's sort of a starting distorted wave approach, and you just define the Coulomb part for that. The core interaction is the core target interaction, and it's defined in a very explicit form. So A1 is one of the masses that is used to scale the radius in the way we discussed last week. There could be an A2 if you wanted to introduce an A2. Here it's all 0. So in all the cases there's no A2, and so only A1 was introduced. But if you wanted to define, if the cluster, for example, was alpha-alpha cluster, then you might want to define it in terms of both masses. I don't know. So it will depend on the specific case. This particular case, it's a proton beryllium-7 or proton target, and even the beryllium-7 target only takes into account the mass of the lead. Okay, so RC is the Coulomb radius, and then you've got the depths. So the depth of the real part, the radius of the real part, and the diffuseness of the real part, and then you've got the equivalent for the imaginary part with no surface in this case. So, you know, in this particular case, the interactions, well, in this line you have a spin orbit, which is a different one, and it understands this. If you need a surface one, I can't remember, you have to go back. Antonio, do you remember in this input, if you want to put a surface interaction, how you put it in? I can't remember. If it's WS?
Yes.
It's WS.
Oh, no, WD.
WD. Okay. Okay. So this is the sort of thing that the practitioners know when they need to know, and nobody else. It's actually not written anywhere. But I'm hoping you have control in your standard Fresco input so that you can go back after you run CDC and get your standard Fresco input. You can go back and see what you've defined to make sure, because of course this will be digested in some way, and it may not be the way you want it to be digested. That's why I want you to check that instead of running directly in Fresco. Okay, now a very important little detail is this last one that's defined ground state. That actually is the bound state between the valence particle and the core. And it typically, if you put it ground state, it will take it for everything. So the default is it will use the same interaction for everything. But if you have a different interaction in the continuum, if you want to have a different formulation for the system in the continuum, which very often is needed, because a simple prescription like a single particle model is not able to reproduce all resonances, and if you want to reproduce a resonance you might have to readjust the interaction. So if something like that is needed, then you can add lines to specify that, okay, like a bin option. Okay, any questions about defining the interactions? No? Okay. So once you run CDC with the input that we discussed and produce the output, that's what the output looks like for this particular case. So let's go back and make sure that we understand what we're doing. So remember, we wanted to do boronate breakup on lead-208 with the continuum included from so energy is false, which means it's a momentum grid. It's not going to be even in the energy bins. And it starts at 0.001 to 10 MeV, 10 and steps of 0.5. So the grid is pretty narrow grid. I'm going to have probably many bins included, but all of them have to have the same spin and parity, 0.5 plus, and all of them will have L equals 0, because that's the specification for the spin. Okay? So let's see that we actually did that. Now when we look, now it's a little hard, perhaps you have the screens up there, you might be able to see. It's a little hard, but you'll see here that all of these are states, so it's a whole line of states. There's the standard Fresco name list up here, and then there's a partition defined, and then a whole list of states that are included in this calculation, and all those states have the same spin and parity. All of them are 0.5 spin, parity positive. When you look at the overlaps that are generated, all of them are L equals 0. Let's see if I can find the L equals 0. There it is. So all of them are L equals 0. And they span energies from minus, where is it? Minus 0.0182 all the way to minus 9.5, blah, blah, blah. So binding energy negative means state in the continuum. And it's actually produced a nice little grid for you with all the overlaps that are necessary. Now, there's another little detail here that's called ISC that has to do, in the case of bins, it has to do with the normalization you choose. How do you normalize your bins? I suppose Jeff discussed this in the first day. There's various choices depending on the weight function that you choose. So for resonances, there's specific choices that is advised, and then for momentum bins, there's specific choices. So this is the specific choice. It's standard in momentum bins, L equals 0. So that's typically what is used. And then if you don't know what you should be using, you go to the manual and you find out what it means. What's the weight function corresponding to each of these choices. So overall, this input is no longer that unfamiliar, right? You've seen things like that. They may have not had such long lists of states and such long lists of overlaps, but the standard, numerical method details plus all the potentials. If you look at the potentials, you should be able to identify that these are the potentials you wanted defined in the way, volume plus some real part that's also volume, some imaginary part that's also volume in this case. Final comment here on the last line. There's this line called coupling, and this coupling line contains the type of coupling. In this case, it's kind 3, and kind 3 stands for single particle coupling of the projectile. So we're including single particle excitation of the projectile. If you wanted to include single particle excitation of the target, it would be 4. If you wanted to do transfer, it would be something else. So depending on what sort of couplings you include in your couple channel equation, this number will change. But then associated with each kind, you'll have several choices, and these several choices will, for instance, IP1 will give you the maximum multiple that you're including in your calculation. IP2 has to do with whether it's nuclear, Coulomb plus nuclear. In this case, it was 0. And IP3 is to do with the reorientation aspect. So depending on the case, some of us will actually choose to construct this ourselves and just have these parts pulled out from the CDC run. Okay, because we prefer to have control on this. The good thing is you can always look at that standard output that comes from the CDC and make sure that it's doing what you want it to do. Any questions about these details? So you start with a very simple optical model calculation. The Fresco input is like 10 lines. And we're adding more and more physics, and as we're adding more and more physics, of course it gets more intricate, but hopefully the general structure of it is still all clear. But the devil is in the details, unfortunately. And so you will produce many plots that make no physical sense in the learning process. So you have to question as you go along. Okay. So if you actually take that input that I just had, if you cut and paste and create your own input that looks like that and run it, this is what you get. Well, actually, you don't get this. You get big Fort files, and the Fort files need to be summed up. So what you produce really is a cross-section per bin. But you might want to sum up all the bins to construct an angular distribution, right? If you want to do that, then you sum bins, you put in all your cross-section in, that's the Fort.16 file in Fresco, and it produces a summed file that has an angular distribution in the center of mass of the boron 8. So that's what it looks like. It's kind of wiggly, but as I pointed out, cross-section, because it's a high energy, the cross-section is very forward peaked, you really don't get any contributions at backward angles. So I plotted this up to 5 degrees because I didn't think it was worth looking at anything beyond that. Remember, the calculations were up to 20, so that's pretty safe. Okay, so that's the angular distribution once I summed over all my bins. But I may want to do the opposite. I may want to integrate overall angles and just look at the energy distribution around the bins. Now, it is discretized, and so what these lines represent here is this discretization that is considered. So you may get a sort of irregular plot depending on how broad your bins are. And you may, depending on how nice an energy distribution you want. You may want to narrow down the bins to get more information in the energy distribution. But this is what it looks like. It sort of peaks at a relatively low energy. It's not a resonance. I don't think this system has an L equals 0 resonance. But it is sort of an increase, sort of phase space effect that you get a maximum at small energies. Okay, and this is how you'd get such a plot. Any questions here? So essentially the exercise, one of the exercises, the application of CDCC that we would like you to go through will involve the breakup of the deuteron, has one bond state, and then you have the whole continuum, in a rather simplistic way of describing this deuteron. And we will want to look at both the angular distributions and the energy distributions in the center of mass. Okay? Okay, so now I want to walk you through one example. So this is the part on the method. And so this is a good place for us to make sure that you don't have questions. Do you have questions on how everything I've tried to go through on how to actually do a Fresco calculation, CDCC Fresco calculation? No? You sure? It will all come in the afternoon. I see. Okay. So then I want to walk you through a case with a lot of detail, looking at many different things, okay? And I picked a case that I've looked at before, and so I had this information at hand. And it's a case that has astrophysical interest. So the beryllium-7, how it's formed in the stars depends on how much it's formed in stars depends on this reaction, the helium-3 alpha-gamma. And this reaction at low relative energies, which are the relevant energies for burning, for alpha burning in the stars, this reaction has a very small cross-section, so it's hard. People find it really hard to measure directly. Now the lunar collaboration has meanwhile measured it quite accurately, but people often use indirect methods to try and extract this rate. One method is through Coulomb dissociation. So if you look at the inverse process, you've got beryllium-7 coming in, you break it up as an alpha plus helium-3, and you look at the inverse process. From the inverse process, you can infer the direct process. Of course, it's a more complicated process because now you've got this heavy target, perhaps a lead target, and you have to control the reaction dynamics, you know, what's happening in the reaction and making sure that what you're measuring really translates to the stuff that you're interested in. So that's one method, the Coulomb dissociation method. Another indirect method has to do with the fact that at these very low energies, alpha helium-3, the relative motion between alpha and helium-3, the magnitude of the cross-section is basically determined by, the cross-section, I need to be more clear. The capture cross-section, this cross-section that I'm talking about, the magnitude of this cross-section at very low relative energies is essentially sensitive to the tail of the relative motion wave function between the alpha and the helium-3 of the beryllium-7. So if you know the asymptotic normalization coefficient, which I think you've already discussed in day 1 or day 2, I don't know, I wasn't here yet, but I know that you already defined what the magnitude of the tail, this term asymptotic normalization coefficient. So if you know that, then you know the overall scaling of this, and that's another method that is used called the ANC method. It typically involves lighter targets and low energy so that the reaction is peripheral, and then if you're sensitive to just the tail, you extract that quantity from your data. So these two methods are standard methods that are used to extract astrophysical information, and in particular it was thought that perhaps could be used for the beryllium-7 case. Okay? Now we want to, they both will involve some sort of breakup calculation, and so in one case you do the breakup because you want to be Coulomb dominated, you want this to really be sensitive to the Coulomb transition. so that you have a direct relationship to the Coulomb transition involved here. So the electromagnetic transition involved here takes you directly from a continuum state alpha helium-3 to the ground state. So that's the Coulomb dissociation method. And then the ANC method tries to get just the scaling factor, this overall normalization that comes from the tail of that cluster wave function of beryllium-7. So I think a few comments about the two approaches before we actually go to the calculations and we discuss the calculations, because that's basically what I want to do. So in this case, in this picture, where you essentially have a large, heavy target that produces a lot of photons, virtual photons, and these virtual photons excite the beryllium-7 into the continuum. In this case, there's a number of complications. The obvious one is nuclear. In addition to the Coulomb, you will have nuclear interfering in your process. There's also the fact that the original cross-section you're interested is at the low energies of interest is dominated. It's basically an E1 transition, whereas this process will also have E2 contributions. So by E1 and E2, do you know what I mean? Do you know what I'm talking about? Okay. So we're talking again of multiples of the couplings, and so there's different multipolarities that I can include. And then finally, there's also final state interactions here with the target that of course don't exist in the real reaction because there's no lead in the reaction of interest. So these are all complications that you have to deal with when you use the Coulomb dissociation method. In the ANC method, you relate the cross-section from experiment with a cross-section from theory with a normalization factor that is related to the ANC. And if you remember correctly, the ANC comes from the tail of the overlap function. At very large distances, it goes as a Whittaker function of R times some normalization, and that normalization is what is called the ANC. And so what you need to ensure is that your cross-section from experiment is only sensitive to that tail. Because if you're sensitive to the anterior, then it's not a good way to scale your cross-section. So that's the condition for this method to be useful. So it motivated an experiment of beryllium-7 on carbon at 25 MeV per nucleon. So the previous one, actually, there was an experiment at NSCL of beryllium-7 on lead at 100 MeV per nucleon. Okay, so we know what the method is. The method is a three-body method. We start with a three-body Hamiltonian. We expand in the eigenstates of the projectile. So the projectile is defined by bound states and continuum states, and we bunch up the continuum in these bins. You know, this is basically what I've been telling you for a while. How we do that depends on the structure of your continuum. So in this particular case, where you've got beryllium-7, we know the spectrum of beryllium-7, and we know it has some resonances. And one of them in particular falls in the low-lying energy scale, and so you need to worry about it if you're going to do breakup calculations that are accurate. Here it is. It's treated differently. That's what it means here. So you include in this calculation, this model calculation, there are two bound states. Beryllium-7 has two bound states, and we include both. They are dominant P3/2 and P1/2, and so they're modeled in single particle form in this way at the right energies. They adjusted to produce these energies. And then we put a continuum there, and here it is assumed that we include L equals 0, L equals 1, L equals 2, and L equals 3 in these calculations, right? It was found that this was enough for convergence. But in principle, how many of these you include will depend on convergence of the problem. So you have to check how many partial waves do you want to include in order to get your converged calculation. As I pointed out, there's a resonance, F7/2 structure, and so it needs to be included properly, and there's a different weighting in that bin taking that into account. So in total, if you sum these all up, it's 72 coupled channels. So that's the calculation that is done. You solve that equation with 72 coupled channels. Okay? And we know that, so I don't need to go through it. There's physics that has to go in. And so this is where you need to know your systems and know the spectra, the properties, so that you can find the right way of defining these effective interactions that capture the most important physics. I mean, you know that you're not going to be describing the problem exactly because it is a many-body problem by nature. So you're going to make approximations, but you need to have some of the features of the system need to be right. You better get your angular momentum in the relative motion right. You better get the size of the system overall right. You know, there's things that you need to get right. And you can look at what is known. And sometimes you're working on objects that are not known. Nothing's been measured about these objects, and so you don't know anything, and so you can just make it up. But if there are things that are known about the system, inform yourself about that, and then use it to constrain the interactions. So in this particular case, there's a bunch of things that were known and that were used to constrain the interaction, okay? Because beryllium-7, well, actually, not so much is known on beryllium-7, but quite a lot is known on lithium-7, and because of the symmetry between the two systems, one can construct something that looks pretty constrained, that isn't as free as you might think if you put all the parameters running freely. Okay. Did you talk about Pauli blocking, Jeff, anywhere? Did you talk about Pauli blocking and the fact that some wave functions, you have to have a certain number of nodes?
Yes, we discussed the
Good.
nodes within an oscillator picture.
Okay, good. So go back to your notes on the first day and think about, you know, what states would be allowed in the beryllium-7 system if you break it up in a cluster of alpha plus helium-3. I mean, you're going to have certain conditions that you have to satisfy in order for these nucleons not to be occupying, not to break the Pauli condition. Okay, so go back. I don't need to spend time here now. As I pointed out, typically the cluster target optical potentials are taken from elastic scattering. And very often they may not be available for the case you're interested, and so you then have to make informed choices of what you're going to do. I mean, I need an optical potential for, let's say, something odd, carbon-21 on lead-208. Now, no one has measured elastic scattering of carbon-21 on lead-208, so it's not going to be very helpful to try that. But perhaps they've measured carbon-20. Probably haven't. That's the closest thing they've measured is carbon-12. No, probably there's something closer. But you can either search by thinking this nucleus is not so distant from some neighboring nucleus that has been measured, or you may rely on some microscopic model to produce this interaction. Okay? So in this case it's easy because beryllium-7, the clusterization that we're considering for the beryllium-7 is alpha plus helium-3. So helium-3 and alphas, people have done lots of experiments with these. So there's actually data available in a wide range of energies, and so you can just take it. So this case was an easy one. It's well constrained. Okay, so now we go to the actual calculations. And this is where I want to spend some time because I saw last week some calculations of inelastic scattering and some calculations of elastic scattering that did not look converged. Okay? So already at the level of single channel or two channel, there were things that were not under control in terms of the results. The results were not converged. If the results are not converged, it means garbage. You really can't do anything with those results, right? So no physical interpretation. You shouldn't put any energy in trying to interpret those results. You need to get convergence first. Now, in a CDCC calculation, the effort is much larger. There's so many things that can produce a non-converged cross-section that it's usually the case that you spend a lot more time guaranteeing convergence than actually understanding the final results. But that's okay. You really want to make sure your results are converged, okay? And we know, I mean, some of us do CDCC calculations routinely, and we know that there's calculations out there that are published and that aren't converged, and that's not good because then you're basically extracting things that aren't meaningful. So here's a list, and you can follow this list of all the things that need checking for convergence in a CDCC calculation. So it's a long list. Before, there were only two things. Remember, what were the things you had to check when you did your optical model or your inelastic calculations? What were the two convergence things that you had to check? Please. Number of partial waves. The radial grid. There's basically two things. It's you need to have the radial grid under control, so you needed to have the right step size and the Rmax, and you need to have the right number of partial waves. So those two things are still needed. They'll be somewhere in my list. Bin radius, step, I can't even find it in my list, but it'll be somewhere in my list, okay? Those two things are still needed. It's those two. But there's a bunch of other things, okay? And so there's number of multiples in your potential. Now you've got coupling potentials, you expand this in multiples. How many multiples do you include? You need to check. Maximum radius for the coupled equation. So remember I told you that the Coulomb is long range and there's Coulomb couplings that are not dying out in this equation. And you can't really integrate this or you shouldn't really integrate this all the way to 9,000 Fermis. You should really find a place, well, it's not 9,000, I'm exaggerating, but it is hundreds of Fermis. And so it's much better to use a formulation, a controlled formulation for this coupled Coulomb functions. So you need to check where that radius should be. And not only do you need to check that R match is right, you need to check that RSM is right, so that you actually carry these couplings to the right place. Then what is the energy that you cut this? Where do you cut this? Here it's 20 MeV. That's pretty large energy. Okay, it's pretty large energy. So don't be shy. Sometimes you do need to go high, right? You're going to deal with a deuteron, so don't start with 50. I mean, you shouldn't start with if you've got an incoming beam. So I can't remember the energy of the problem that you're going to be solving, but I don't think it's very high energy. So if your deuteron comes in with 20 MeV, what's the maximum energy that you can expect that it can excite? It's a very easy question, so don't think it's a trick question. Okay, let's think. I mean, are you just done for the morning, or? So you're bringing in a deuteron, impinging on in a target with a center mass energy, let's say it's 20 MeV. What's the maximum excitation you should expect in the outgoing channel? Sorry? If you give all the kinetic energy to the deuteron and break it, binding energy is 2, so you're left with a little less, right? But certainly you shouldn't expect to be able to break the deuteron. So the Q value for the reaction, in this case, will take the binding energy. So remember that you do have to break the deuteron. But then eventually, you can send all this energy to relative motion, right? So there's already a limiting, you can already, just by looking at the energy of your incoming beam, find out what your limiting case will be. In many cases, you don't need to go that far, okay? So don't start with a very large energy. Do the opposite. Start with a relatively small and include. Now, one thing that helps is looking at distributions, because if you did a calculation and have a distribution, let's take this one, for example. Here it's by partial wave. If you did a calculation, let's say to 5 MeV, maximum energy, and you got a distribution for S waves, you might think, well, I still need some more because I only went up to there. But if you look at the F waves or even the D waves, you realize that you're not where it needs to be. You've truncated it too early and you need to extend. So by looking at the energy distribution, it gives you some clues as to whether the energy you've chosen as maximum energy for the bins is appropriate or not. Okay, so that's the maximum energy. And then, of course, the bin discretization. How fine is this? It does change, and you need to be careful again with resonances that require special care. So how you'll. My advice is always do a calculation with 1 bin discretization, increase it, and make sure your results are not changing very much when you increase it. If you start out with a very small discretization, you pay a high price. The number of partial waves, the number of channels is gigantic, right? So you should take the opposite. Start with a relatively modest number of bins, making bins that are perhaps too broad, and then learn how much smaller they need to be in order to contain the information that you desire. And it will depend on the observable you want to calculate. So that's another point. So I've gone through this list. I've talked about partial waves. Of course, it does depend on partial waves, on the number of partial waves, and you know that, so nothing is new there. It does depend on a step and a radius, a maximum radius. And then it depends on the number of partial waves for the breakup states. So you are expanding in the eigenstates of a Hamiltonian, and there are eigenstates for all else. So the little l is also now an expansion coefficient in a way. You're going to have to truncate this at some point, and in this calculation it's truncated at 3, but there'll be cases in which perhaps only 2 contribute. There might be cases where with 1 you already get a pretty good description. So look at this also for the deuteron, which is going to be your case, and perhaps even think before you put in how many partial waves, think what you expect to be the dominant features in this. Okay, so that's another aspect. And then finally, this is not necessarily, it depends on whether you want the equations to be solved exactly or iteratively. Sometimes people will solve these equations iteratively, and you've got that choice. So the way to solve the equations iteratively in Fresco is, instead of blocking all states with iBlock, as Antonio pointed out, you usually use iBlock to tell Fresco, hey, I want to really solve this exactly as a couple channel. You can solve these iteratively, setting iBlock to 0 and putting iter to a certain number of the iterations you wish to include. And so you, in some cases, if your number of channels is so large, you don't really want to do a full couple channel, but you want something that's iterative, you might get away with having only a few iterations. And then you have to also prove that you've gotten convergence in the number of iterations you've included. Okay? Does it make sense? Or am I speaking complete gibberish? Gibberish? Or? Okay. I'll assume that nods are truthful. So here's an example. So now let's say you did all this. So you did all this list. It took you a couple of days or 3 days. I don't know how many days, but it probably took you a while to go through all these checks. You've got the number of I did forget to say this. In the energy distributions, if you plot the energy distributions for all the partial waves, you can also immediately say whether your truncation in L is sufficient. So what you see here, what you see in these distributions is that S and P are dominant, and then you've got the D's contributing much less, and that particular F still contributes, and this one certainly contributes a lot. So I would argue that we should really be including G's if we wanted a full exact calculation. So it's not going to be as important, it's going to be less important than the D's. It's going to be, it was found to be very negligible for the observables we were looking at, but just based on this figure you could think, well, perhaps I should check G's. L equals 4 in my expansion. So this figure will help you also determine whether the number of partial waves are enough. Okay, so now you've done your calculation. You've got converged results. You've got results that you believe, and what can you learn from those results? What physics is included in this breakup? So I want to discuss then the 2 extreme cases. We had one case in which we were going to try and extract a capture alpha gamma reaction producing beryllium-7 from the Coulomb dissociation, heavy target, high energy. And we were going to do a case on a light target at low energy with the hope of extracting an asymptotic normalization coefficient. So now let's look at these two cases and see whether it's okay. So the beryllium-7 on the lead produces cross-sections that are forward-peaked. Well, there's no surprise. At 100 MeV per nucleon, you expect it to be very forward-peaked. And what is shown here are the effects of couplings. So if you solve the full CDCC, you get this black curve. If you do just DWBA, you get that red curve. If you solve this but include no continuum in the couplings, then you get this blue curve. And it really shows that all these couplings actually are doing something, and you should be including all these couplings. It just shows to what extent you'd be away from that result if you neglected some part of the problem. The same exercise can be done for the other reaction. And actually, before I go there, what do you expect? Do you expect the effects of couplings to be larger or smaller if you reduce the energy? Is there an expectation at this point, or you don't have an idea?
Smaller, perhaps?
If you reduce the energy, smaller. Okay, well, that's something to think about. So if the reaction is, so what's the time scale for the reaction to occur if the energy is very, well, is the time scale larger or smaller when you reduce the energy of the beam? You increase your time scale for the reaction. So you really allow it to change, to readjust to the dynamics of the target, right? So think about it, because this will be useful when you change the energy in the homework this afternoon, right? There's one energy to start with, and then you change it dramatically, and you're going to have to make some conclusions out of that. So coupling effects are larger at these energies, and it is according to my expectations. Okay, now remember that the idea of this ANC method is that you're only sensitive to the tail of the wave function. So the reaction really has to be peripheral. If you're catching the interior, then it's not fair to do a scaling with the ANC. It's not the right way to do it. So in this particular case, what you can always do, I mean, actually you can do it, is plot the cross-section as a function of J, as a function of the partial wave. And some of you did this already for the elastic and the inelastic, and you can certainly do it for the breakup. You will have some distribution as a function of J that has a certain peak at some point. Now, the fact that if you relate this to impact parameter in a semi-classical picture, if you relate this to impact parameter, then the surface of the nucleus would be somewhere here, which means you're actually catching quite a lot from the interior for this reaction. So what we concluded was it was about 28% of the breakup cross-section was actually coming from impact parameters smaller than what you'd wish if you wanted to extract an ANC. So this would be an error that would come with the extraction of the quantity that has nothing to do with like uncertainties and potentials and so on. It has to do with the actual method, indirect method you're using to extract this quantity. Okay? So this is a way to understand what's going on, although I should really say this is a semi-classical picture, and it's not necessarily very accurate. It just gives you an idea that you are catching the interior. Now, on the other hand, the Coulomb dissociation method, the condition is that it's nuclear free. It's only Coulomb. Why did I say Coulomb free? Oh, no, sorry, we're still on the other reaction. So the question here is, does it have a lot of Coulomb? Is it just nuclear? And you can do that very easily by turning this variable, and you can just run a calculation with just nuclear, run a calculation with Coulomb plus nuclear. Now, traditionally we think heavy targets, they have a lot of charge, they Coulomb dominated. Light targets like carbon-12 they have a small charge, so it's nuclear dominated. If I calculate something that's just nuclear, I may still have pretty good results. That's close to the full thing. So this is how close it is. Just nuclear and total, that's the difference. So there is a little difference. I mean, it's not dramatic, but there is some difference. And what is also shown here is that point that I made probably in the first day on Wednesday last week, that you can't add these incoherently. You can't do a Coulomb calculation, do a nuclear calculation and sum them, because what you get is something that's very different. Okay? There's interference that is important between these two processes. Okay, then the question, I thought I was talking about this, so in the Coulomb dissociation you want it to be nuclear free, and so you can do similar test in this particular reaction. So if you run this for Coulomb plus nuclear and do a CDCC calculation just including the Coulomb, do you get the same answer? And the answer to that question, if you look at the dashed and the total, obviously there's a difference between those two, right? And that difference is going to be important mostly in the interior region, you know, for the small partial waves where the impact parameter is low, as you expect, because the nuclear interaction is not the long-range thing. So in the long-range region, it's basically nuclear. But there is a part that's contributing to the cross-section, it's not negligible, that has the nuclear. So in particular here, it is found if you think of an impact parameter scattering angle of 2.5 degrees, and the impact parameter that relates to that, it's out here. So you could say, I need to only keep my data between 0 and 2.5 degrees in order to have Coulomb only. And that's the sort of game that is played with the experimental data, is what is the region in the angular distribution that is just Coulomb? And then you just use that, you now analyze that data to extract the information you're interested in. Sort of somehow selecting the data according to a reaction theory model. Make sense? Okay, well, of course you could take it further now and say, well, that's a sort of a semi-classical approach. Let's actually look at the angular distributions in detail. So if you look at the angular distributions in detail, what it tells you is that the nuclear and the Coulomb actually, it's not zero. The nuclear is not zero at all. It's still contributing. But when you have integrated cross-sections, you multiply by a sine theta, right? So the d omega is a sine theta d theta. So that for integrated cross-sections is not going to make a large difference, those small angles. But if you're actually looking at angular distributions, you might be able to see a large difference. Okay, finally, in this particular case, people really wanted to make sure it was really only Coulomb. And so they sort of a different way, not only would they limit the angular range, they would limit the energy range. So if you limit the energy range, so let's go back. What do you expect? Do you expect larger contributions from E2s from which energies, which relative energies? So I'll bring up a figure that might help in answering the question. I'll pose the question again because I think it was very unclear. Okay. So you have multiple different transitions that are happening in this reaction. You're breaking up the beryllium-7 on a lead target, and you have different multiples that are contributing. The reaction you want to extract really is the capture alpha-gamma reaction that is only sensitive to E1, to one of these transitions. So where in the energy, relative energy of the projectiles, do you expect this to be dominant? Okay, perhaps it helps if I tell you that the ground state of beryllium-7 in this model would be, well, it is a relative p state between the alpha and the helium-3. So you've got a ground state that's L equals 1, and now you want to capture a transition that is E1. So what's the final S? What is the final L? I guess I answered L equals 0, right? It could be L equals 2 as well. But to lowest order, you'd have L equals 0. So that would be the place. And where does it peak? At low relative energies, right? So if you manage to capture just the low relative energies, you might be able to isolate the contributions coming from E2. What is the final L of the E2? So if you start from an L equals 1 state in the ground state and you want to break it up through an E2, what's the final? Sorry? It could be F, it could be P, right? But it's going to be shifted, right? So if you keep it down, then you might have a hope of reducing that E2. And so that's the sort of thing that you can do. You can control what you're getting. So if you keep it to small relative energies, it turns out that you completely hinder nuclear and you hinder the E2, which is the thing that I was talking about. Okay, so this is just multiple features of how you, after you've actually done a breakup calculation with full space, you can now constrain what you're getting to extract different sorts of information. Okay, this is more of the same. I think now you're going to see, I think this plot will come back when Antonio on Wednesday comes to semi-classical methods. Right, you're going to show something like this? Okay, so then I won't discuss it, okay? But you'll see that there's other ways of approaching these reactions with semi-classical methods that don't involve solving these quantum mechanically based coupled channel equations. You can also do some coupled channel that are now based on trajectories of these of the center of mass of the projectiles, and in that formalism you get approximate answers that in some cases are actually a good approximation, in some cases they're not. And so Antonio will discuss that, I'm sure. Okay, so now I want to know, what time is it? Where am I?
Nearly 20 past 12.
20 past. Okay, so I'll briefly talk about three-body observables, and then we'll stop. So far, everything I've shown are what I would call center of mass observables, two-body observables. We require the experimentalist to measure both the projectiles, both fragments that come out of this breakup, and reconstruct the center of mass, right? Because everything I did was in the center of mass variable. So the theta center of mass is not what they actually measure. The theta of the center of mass of the boron-8 or the beryllium-7 is not what was that they measured a scattering angle for the alpha particle coming out and a scattering angle for the helium-3 coming out, not the center. So if, of course you can reconstruct, if you have full kinematics, you can reconstruct and construct those observables, which we theorists like. But very often, you might not have all the kinematics to reconstruct that. If one of the particles that flew out was a neutron, you might not have a neutron detector. You may just be measuring charged particles. Or you may just be measuring the neutrons, or whatever. So, and there's other aspects, other details that you can look at. If you decide now you're going to look at triple differential cross-sections, quadruple differential cross-sections, where you now want to look at the distribution when the proton is coming out at this angle. What does it look for the core? So there's a lot more detail that can be constructed that we didn't construct because we were focusing on these center of mass two-body observables. So what I'd like to say is that once you solve a problem like this, and you extract your T matrix, which is truly a T matrix now, and it's got all these channels in there, you've got the information to construct much more than just these center mass observables. And so you can, from there, extract the full solution and of course then think about what is the physics of the experiment that you want to compare to and construct the observables accordingly. So I'd just like to mention that. The scattering amplitude that we had, well, I guess now it's a lot, Antonia has gone through how it carries all these spins and it looks much more intricate, but again it relates to the S matrix that we discussed before, and it will contain angular information of the various things coming out. So typically you will calculate the projectile wave functions, you calculate the coupling, you solve the coupled channel equations, and you get your S matrix and your scattering amplitude. And now you can construct your observables. So let's discuss how to do that. Now I worked out some form of the T matrix. When you construct the vector form of the T matrix, it has this form that I think was actually on the board a while ago. If you now have bins, you can actually work out how they look like compared to bins. So you put a full set here of bins, and then you get this term here that comes out directly from your coupled channel solution, times this that actually relates the overlap of this bin model wave function with the real thing. And so you can construct a T matrix that then you can use to construct the observables you're interested in. And of course it's fun. I don't know that Jeff, was this a homework ever to actually look at the bins in plane waves? So the projection of the bins? Yeah. Okay. So if you have nothing else to do at some point and want to work out, this can be worked out. We haven't, and it's in the single particle case. It's not a daunting task at all. Okay. So what I want to say now is now you've got all the information contained in the C matrix. You can construct anything you want, and in particular, let's say you want to construct this triple differential cross-section because the measurement that you're interested in analyzing has measured the energy of one fragment and the angles of both. Okay, so you've got information on the energy of one fragment, not two, and you've got the angles of both. So you could actually compare to things like this. The data contains things like this. So how do you do that? Well, you have to sum over all relevant projections your T matrix squared times the phase space. And in this particular case, the phase space has to get the right energy and the right momentum because you've got the direction, you've got the angles. Okay? So you construct this and you work out what this looks like, and in the end you've got efficiencies usually that you need to take into account. So as a theorist, we usually don't like to deal with efficiencies, but if the quantity that was measured is measured differently for different energies, then you better put in the efficiencies. If your detectors have a finite size, you better put in the resolution of that because it does make a difference in the comparison. The minute you really want to compare to data, you need to know these details to make that comparison meaningful. Okay, so in this particular case, I said we only measured the energy of one, and so here it changes. Let's say you only measure the energy and the angle of one particle. So you need to integrate that triple differential that you had before. It has a certain solid angle, and it's got an efficiency that depends on angle. So if this was the case, then you'd construct an observable that would be integrated over the other particles' angles. You'd take into account the efficiency of the thing that you measured the angle of. So you take into account that efficiency, and you take into account the angular resolution because you have certain solid angle. And so you'd construct an observable that relates directly to the thing that was measured. Okay. So we've discussed model space. I think I can stop here. Is that, are we sort of 12:30? Yeah. Okay. So let's stop here. And I wish you luck for the deuteron breakup calculations this afternoon.